Friends, welcome back. Last session we had seen the problems associated with the lock. The major problem with the lock is when the resource is not available, then the process requesting that resource cannot enter the critical section and it keeps waiting. Waiting means it gets into an infinite loop or a loop, and this loop means it's executing nothing but simply wasting the CPU time. So instead, when we know that the process cannot proceed further because the next step it has to work only in critical section, and as long as it is not allowed to enter the critical section it cannot proceed further, and when we know this, then there is no point in keeping that process in the ready state or the running state. Instead, we can just move it to the blocked state. By doing this, the processes which were not allowed to continue no longer compete for the CPU till they get a required resources. So they keep waiting in the block state, not in a running state, and hence no more wastage of the CPU. So that's how the semaphore works for. Semaphore is a synchronization tool used to control access to the shared resources by multiple processes or threads in a concurrent system. So that means when multiple processes or multiple threads are trying to compete for some shared resources, then we need some synchronization tool, and that tool is a semaphore. The main purpose of defining a semaphore is to ensure that the CPU time is not wasted by any process which is not possible to enter into its critical section. Instead of waiting, we can make that process blocked. So the semaphores help in preventing the race conditions. Yes, of course, it will ensure that any given time maximum one process or one thread will be in the critical section, and that thereby race condition is prevented. It manages the critical sections properly and ensures that the mutual exclusion or the coordination among the processes is properly maintained. So at the implementation level, if we look in semaphore, S is an integer which usually is equal to the number of resource instances we have. For example, printer is a resource, and the printer can be used by multiple processes or multiple threads, so we can call it a shared resource. But the major problem with the printer when allowed to used by multiple processes is to ensure that any given time only one process should be printing on the printer. Otherwise, the printed matter may get mixed up and makes totally no sense. So when one process is printing its document, till that document printing is complete, no other process should intervene. That's what we talk about mutual exclusion. So in the network, if we have say 5 printers, then we initiate the value of S with equal to 5, where this S is for the printers. Printers are the shared resources in our system. So 5 printers are being shared by processes, so S is 5 to start with. And the major thing here is not just value of variable S, it's another important thing is this value S or this integer S can be accessed by only 2 atomic operations. So there are only 2 operations that can access this variable, and both of them are atomic in nature. What is atomic? Either total or none. So fully executed or nothing is executed, that's what we call atomic operation. and these two atomic operations are wait and signal. So before entering into any critical section, the process should wait and see whether it is free to enter the critical section. If it is so, it will enter the critical section and ensure that others are not allowed to enter the critical section. Some way it has to be done. And when a process which is using the resources which is in the critical section, once the critical activity is over, then it must release the shared resource, and that release is done through another operation called signal. So wait is one which is used to reserve shared resource for usage, and signal is one which is used to release that shared resource. These two are used. So one simple way of implementing this is wait yes. So as long as yes is negative, so do nothing. If yes is positive, then decrement yes. So we started with 5 printers. Some process wanted a printer. So what is yes? Yes is 5, greater than 0, done. So that printer allocated to that process. Now we are having 4. So what happened? Yes is subtracted by 1, yes minus minus, now we have 4. So to start with, yes was 5, which is greater than 0, therefore that while loop does not work, directly gets into the next line, yes minus minus, it becomes 4, comes out of that, and then gets into the critical section. After critical section, we have one which is called signal. Signal is just incrementing the value of yes plus wait. This wait here still has that danger of lock. It is waiting. That means there is a while loop here doing nothing. That means this is wasting the CPU time, and that's not what semaphore is. So semaphore is something different. So we have 2 types of semaphores. One is the counting semaphore, other is a binary semaphore. Counting semaphore is used when we have multiple identical resources of any type, and a binary semaphore is used when we have a single copy of that resource. So let's check what a binary semaphore is doing. That's a mutual exclusion, mutex. So this is used for protecting the critical section, allows only one process or thread at a time to enter the critical section. So that's what before getting into critical section, we just wait, and if wait condition is false, then gets into the critical section. Once critical section is done, then we signal. So wait means looks for the shared resource we are interested in. If it is available, then gets into critical section, locking it, and once we signal it, then that particular critical shared resource is released. Now coming to the counting semaphore, initialized to a value n which is greater than 1, where n is the number of identical resources available. In our previous example, 5 printers were available, so n is equal to 5. And each time process accesses one resource, a wait is called that decrements this counter. And then when that process completes the critical section, then signal is called, which increments the count. If the count reaches 0, then any new process calling wait will be blocked until the resources are released. So initially we had 5 printers, all 5 are free, so n is equal to 5, s is equal to 5. Then one process wanted to use a printer, so one of the 5 printers allotted to that process. So the number of printers available for usage is 4 now, and one more process wanted, now available 3, one more process wanted, available 2, one more process wanted, available 1, one more process wanted, available 0. So 5 processes used 5 printers. Now when the 6th process comes in, there is no printer available, therefore it has to wait till one of the earlier 5 processes release a printer. Till that, the 6th one has to wait. Not necessary that only one is coming up. Maybe 10 more processes want to use the printer. 5 were available, 5 were allotted. After 5 allotted, the value of S had gone to 0. After that, 10 more have come in. Then it went on reducing, and finally it goes to -10, which says that 10 have asked for a printer. So how this makes sense? So let's take up. So for every resource we have one list. For every resource we have one list which is used for storing the waiting processes. So we have a list which stores the waiting processes, and we have a value, how many processes are waiting, or what is the value of the semaphore. So when a process wants to use a shared resource, it will call for the concerned semaphore wait. It says wait for printer. There were 5 printers, so first thing happens, the value of that semaphore was 5 to start with. So first process calls for request to the printer. It calls wait semaphore corresponding to the printers. 5 printers were available, so it first reduces by 1. So now the value of printers is 4, and if it is less than 0. So please note here that the comparison is done after subtraction. So first 5 were there, reduced, become 4, but still 5 were there. Then next time 4 were there, as you enter, reduced. Then 3 were there, the moment you enter, reduced. 2 were there, the moment you entered, reduced. And 1 was there, the moment you entered, reduced. So even then all 5, the 5th process, if you look at it, the value was 0. So first process it becomes 4, second process it becomes 3, third process it becomes 2, fourth process it becomes 1, fifth process it has become 0. But sixth process 0 goes down to negative. So sixth process should be stopped, not up to fifth process. Sixth process should be stopped. Therefore, if value is less than 0, that means if it goes negative, then add that current process to the list and then block it. Don't wait. Just the process which is trying to use that shared resource, if it is beyond the total number of resources available, then it has to wait. So before blocking it, make sure to remember which was requesting, so put that in the block list. So we have a list for that particular semaphore. So add to that list and block that process. Done. So that process is no more executable. It goes into the block state. So please remember the initial lectures about process management, where the state of the process running ready block, yeah, it goes into that block, Until it is unblocked, it cannot get into ready. Until it is ready, it cannot go to running. Therefore, there is no question of getting this process any execution time. So no more CPU time wasted for this particular process because it goes into the block list. Okay, how does it come out? It comes out when some of the 5 processes which had occupied these 5 printers completes its printing job. It says signal. The moment it says signal, that printer gets released. And the moment a printer gets released, the value gets updated, incremented by 1. Because one more printer is free now. So far, so good. Now, what to do next? Next is to know, is somebody waiting for it? Is somebody waiting for this resource or not? If none of them are waiting for the resource, just neglect it, don't have to do anything. So we have to do something only when somebody else was waiting for this particular resource. Therefore, look for the value of yes. So as just discussed here, the 6th process onwards, they keep decrementing the value, therefore the value goes negative. So any process waiting, it means that value has to be negative. If the value is 0 and above or above 0, it means that no process is waiting. When no process is waiting, then whom should I wake up? I don't have to wake up anyone. Therefore, once one resource is released, then the value is updated, incremented by 1, and then look at value. If it is negative or 0, which means that some process was waiting. Because here the first waiting process made the value -1, and next waiting process continued to make it more negative. So assume that it is the first waiting process which has made it -1 because of this, and the moment you signal, it is incremented, so this -1 will become 0. Therefore, I have to check for 0 also. Even if it is 0, which means that at least one process, if it is 0, it means one process was waiting, wake up. If it is less than 0, then at least one process is waiting, so remove one process P from that list and wake up that process. So that's as simple as that. So don't keep waiting. Anytime process doesn't get a resource, keep that in the block list. When that resource becomes free, the blocked process wake it and give it the resource to continue. So this way we can ensure that the race condition can be avoided anytime one be in the critical section for that particular resource and so on. So here yes is a semaphore for a resource. So for every resource 1 yes. So for printer 1 yes. For such other things another yes, and so on. So most important here is, so when I say wait, so it has to be subtracted. To subtract 1, as we discussed in the beginning, at the register level it is 3 instructions, so all 3 have to be executed at a time, and then check the value, then add to the list, then block. All these operations at the processor level need many operations to be done, and we don't want midway the process to be stopped and some other process start continuing. Therefore, this all the instructions in the wait either totally executed or totally not executed, so that is atomic action. Same thing with the signal. Both these operations are atomic in nature. So let's take up an example. So for any given resource, 4 processes are already in the waiting list. So some have already gone. One process is currently using the resource. Then P1 had come, P1 entered the waiting list, then P2 came, P2 entered the waiting list, then P3 came, P3 entered the waiting list, then P4 came, then P4 entered the waiting list. Now P5 executed wait. Now P5 wanted to use this shared resource, so it said wait, then P5 gets into the waiting list. So this is the waiting list for that particular resource. So somebody is already using that resource, and once that usage is done, then it will give a signal, say that my usage is done, so I am releasing that particular resource. So the moment that resource is released, then this one which was waiting, P1, is woken up. So that's how the whole process is done, wait and signal. Here we are not using that loop function here. It's not wasting the CPU time. We just dump it onto the queue, semaphore queue. So each semaphore will have a queue, and for each shared resource will have a semaphore. So depending on the number of instances of the shared resources, the value of semaphore will be fixed. It may be counting type or binary type, and if it is counting type, then that's what happens. Even if it is binary type, that's what happens for every shared resource, one semaphore, and we have one waiting list. And processes that could not get the shared resource get it to the wait list because they are blocked. And the process P1 was blocked some time back, and when the resource is available now, then P1 is woken up and said that now get up, go to the ready state, and the scheduler will decide when this P1 gets its chance. So as per the scheduler's activity, P1 will come into the ready state. From the ready state comes to the running state, and once it comes to running state, the shared resource was available, so it gets into the critical section, and once it gets into critical section, then others are locked, stopped. When it leaves, then P2 gets its turn. So that's how things work. So that's it about the semaphores. Thank you.